Good morning, dear student. In previous lecture, we will discuss the Higgs coupling reaction. So, in today's lecture, we will discuss the second important type of CC coupling reaction, that is Suzuki coupling reaction. So, what is this Suzuki coupling reaction? This is an organic coupling reaction where the coupling partners are boronic acid and organohalides. So, if we consider a general reaction, that is RX, so this is your halides, and the second partner is your boronic acid. So in this case, one of the hydroxyl group of boric acid, it is replaced by the R dash group. So this is your boronic acid and RX, that is halides, in presence of base and catalyst such as PD0 to give the CC coupling reaction, that is formation of R dash as a product. So what is the importance of this reaction over all other coupling reaction is that if you consider this Rx means it may be either sp2 or sp3. So we'll discuss in earlier that in Higgs coupling reaction, whatever the halogen is there, it should be unsaturated halide should be there. Unsaturated halide should be there for reaction. So the halide must be attached to sp2 carbon. So in Suzuki coupling, there is no such a condition that the halides must be sp2. Uh, Unsaturated halide means it is attached to sp2 carbon. So either it is attached to sp2 or sp3. Either it is attached to carbon carbon double bond or carbon carbon single bond. So this is the advantages. This is the advantage of Suzuki coupling over other coupling reaction. Similarly, this boronic acid, it may be sp2 or sp3. That is the group which is attached to boronic acid, it may be either sp2 or sp3. So if you consider a general reaction, so this is your halides, so this is your sp3 carbon. So if you consider this carbon number 1 is your sp3 carbon, okay, so it is a single bond between carbon and halogen. And similarly, if you consider this second component of this Suzuki coupling reaction is boronic acid. So this carbon is attached to this boron, it also having sp3 hybridization. So this is your important points regarding to the Suzuki coupling reaction, that it is not necessary that halides and the group, that is the second partner, must be sp2. So in Higgs coupling reaction, the second partner is carbon carbon double bond, that is alkene, and one is unsaturated halides. So this is not the conditions for this Suzuki coupling reaction. Halides may be sp2 or sp3, and the boronic acid may be sp2 or sp3. So you should remember halide is same. So what is the difference? Instead of alkene, that is in Higgs coupling reaction, the interaction between halides and alkenes. So in this case, the interaction between halides and boronic acids. So what is the difference? Only the alkene is replaced by the boronic acids. So let us discuss the mechanism or the catalytic cycle for this Suzuki coupling reaction. So let us discuss the mechanism or the catalytic cycle for Suzuki coupling reaction. Again, when you consider any catalytic cycle, the first step of this any catalytic cycle is oxidative addition. Again, the active catalyst is used in this case also, the palladium, that is PdL2. It is in zero oxidation state. So the actual catalyst is PdPPH3 4 times, but it is inactive form of catalyst. Therefore it undergo dissociation of 2 phosphine ligand and to form PdL2. So L stands for phosphine ligands, PPH3, which is 2 electron donor. Again, if you consider this is your palladium, it contribute 10 electrons, and these 2 phosphine, that is L stand for phosphine, contribute 4 electrons. So this is your 14 electron species. So this is the active form or active site of the catalyst which is used in this Suzuki coupling reaction. Again, if you consider the first step of this Suzuki coupling reaction is the oxidative addition. oxidative addition. So what is oxidative addition? Oxidative addition is nothing but the insertion of metal atom between a single bond, that is the bond between so in this case the bond between carbon and halogen. So there is no limitation, either the halides may be sp2 or sp3. So in this case we consider again sp2 sp2 halides, that is unsaturated halides. Oxidative addition same as a Higgs coupling reaction, that is bromobenzene. So okay, bromobenzene. So this is your sp2 carbon. So this is your sp2. So these halides are unsaturated halide, either it may be sp2 or sp3. So the first step is oxidative addition, and what is going on in oxidative addition? Just insertion of metal atom between this carbon, sp2 carbon, and this bromine atom. So what is the product? Here we get pd l l, one of the bromine is there and one of the phenyl ligand is there. So we can write pH as there. So pH stands for phenyl. So you should remember pH. What is pH? It is phenyl, C6H5, C6H5. Okay, so this is the first step. So the next important points of this mechanism or this cycle is that the role of solvent is very important in Suzuki coupling reaction. So the first step is what? Oxidative addition of unsaturated halides to this active catalyst, that is PDL2, to form a PDL2Br pH. So 14 electron species is converted into 16 electron species, and there is a change in oxidation state of this palladium from 0 to +2. So if you consider this palladium and bromine bond, so if you consider this palladium and bromine bond, it is a strong bond, because we know that this bromine is electronegative and the metal have much more positive charge. Therefore the bond between this palladium and bromine is a strong bond, because it is bromine is more electronegative, and therefore there is a strong bond between this metal atom and bromine. So strong bond is there, and due to the strong bond, if we consider the rate of transmetallation is much slower when there is a bond between this palladium and bromine atom. So due to the strong bond, more energy is required to dissociate this bond for further reaction. That is, the next important reaction of this catalytic cycle is transmetallation, and due to the strong bond between this palladium and this bromine, so this bond cannot dissociate immediately. So it is a very strong bond, and therefore the rate of transmetallation is very slow, and we require a lot of time to get the final product. So what is the role of solvent in this case? So the role of solvent is very important. So for example, let us consider in this case the solvent is tertiary butoxide, potassium tertiary butoxide, potassium tertiary butoxides, K positive O, TBU having negative charge. So this is your solvent, not solvent, this is your base. So the role of base is very important, not solvent, this is your base, that is the reaction in presence of palladium as a catalyst and base. So this is your base, that is potassium tertiary butoxide. Its role is very important, because this potassium tertiary butoxide, it can easily replace this bromine. So it will substitute this bromine, and what you get here? We get here PD. This is your, let us consider this is as your pH, this is LL, and this is your OTBU, plus what you get here? KBr is there, KBr formation is. So the substitution of this bromine atom by this base, that is potassium tertiary butoxides. So we know that this palladium and this bromine bond is strong, and therefore the rate of transmetallation is very slow. But due to the presence of base such as potassium tertiary butoxides, this potassium tertiary butoxide replace the bromine by itself. And if you consider, we know that oxygen is more electronegative. Oxygen is more electronegative. So if you consider this OTBU, so oxygen is more electronegative, and therefore if you consider, uh, due to the high electronegativity, the bond between this palladium and this tertiary butoxide, that is the bond between palladium and oxygen, it is weak bond. So this is a weak bond. This is a weak bond. So the first step is oxidative addition. After that, if you consider, the electronegativity is very high for this bromine, and the net positive charge on this metal atom, therefore it is a very strong bond. And due to the strong bonding between this palladium and bromine, it does not dissociate immediately, and the further transmetallation step, it is very slow. The rate of transmetallation step is very slow in the catalytic cycle of Suzuki coupling reaction. But presence of base, the base is replaced this bromine atom, and oxygen is more electronegative as compared to bromine, and therefore the bond between this palladium and this oxygen is very weak bond, and therefore due to this the rate of transmetallation is very high. The rate of transmetallation is very high. So student, you should understand why there is a rate of the rate of transmetallation is very slow, because the strong bond is there and we require lots of energy to break this bond. But in this case, due to the high electronegativity of oxygen, this bond is what, much weaker as compared to this palladium bromine bond, and therefore the rate of transmetallation is higher in this case. So what is this transmetallation? That is transfer of one ligand from one metal atom, one atom to another atom, either it is non-metal to metal, metal to metal. So transmetallation, transfer of one ligand from one atom to another atom, it is called transmetallation. So this is what the substitution of bromine by the base such as potassium tertiary butoxides. And due to this weak bond, the rate of transmetallation is very high. So if you consider the further step, before considering the further step, so let us consider, this is your, let us consider this is your second partner, that is boronic acid. So one phenyl is there and two hydroxyl group is there. So we know that the boron, it having a empty vacant orbital. So before discussing, so let us discuss, this is very important point, because you understand. So this is boron, this is OH, this is OH, and this is your phenyl. And we know that this boron having empty 2pz orbital. So what happened, this base such as TBU, potassium tertiary butoxide, when interact with this boronic acid, so it will gives its electron, it will gives its electron, or transfer its electron to this empty 2pz orbital of boronic acid, and therefore after interaction with this potassium tertiary butoxide, the boronic acid is convert, the boronic acid is convert into BOH, OH having negatively charged, and there is a one phenyl group is there, there is a one phenyl group is there, and this is your O tertiary butoxides. So when the base, that is potassium tertiary butoxide, it will interact with boronic acid, and then the Lewis acid, that is boronic acid is the Lewis acid, then the boronic acid is convert into the electron rich species, and it is act as a nucleophile, it is act as a nucleophile, and it can easily transfer and due to the negative charge, it becomes electron rich. It is act as a nucleophile, and it can easily transfer this phenyl to the to the metal atom, that is palladium. So this phenyl, and that is transfer of this phenyl from boron atom to the palladium atom, is called as transmetallation reaction. So you should remember, that is, when this potassium tertiary butoxide react with boronic acid, the Lewis acid, that is boronic acid, it is act as a Lewis acid. So it is electron deficient, but when it react with potassium tertiary butoxide, it becomes electron rich, it having negative charge, and therefore it can easily transfer to this phenyl ligand to the metal atom, that is palladium atom, and therefore this process is called as transmetallation. And the rate of transmetallation is very high, because in this case the boron in this case the bond, we know that the bond between metal atom and the oxygen, that is the potassium tertiary butoxide, when interact with palladium, due to the high electronegativity, the bond is very weak and it can be easily dissociate. So this phenyl can easily replace the potassium tertiary butoxide which is attached to the palladium, and therefore the rate of transmetallation is very high. So this is very important, that is, the role of base in Suzuki coupling is very important. The first role is what? The conversion of strong bond into weak bond, that is replacement of bromine by potassium tertiary butoxide, and after that it will react with boronic acid to form negatively charged species, and therefore the rate of transmetallation is very high due to the negatively charged boronic acid. So let us discuss. So up to this we discuss, that is PD, this is your pH, this is your pH, then there is L, and here the tertiary butoxides, when, so we know that this is your boron, it having vacant orbital. So after interacting with boronic acid, that is, after interacting potassium tertiary butoxide with boronic acid, we get the species, that is the boron having negative charge, this hydroxyl group is there, and one phenyl is there, and O tertiary butoxide is there. So this species is react, that is, due to the negatively charged, it will transfer this phenyl to this metal atom, that is palladium, and there is a removal of this OTBU, that is tertiary butoxides. So the rate of transmetallation, that is transfer of this phenyl from boron atom to this metal atom, it is called transmetallation, and the rate of transmetallation is very high due to the weak bond between this palladium and oxygen. So you should remember. So this step is called as transmetallation. So it is electron rich, and it will transfer this phenyl to this palladium. So what do you get? That is PD, L, this is your pH, O, TBU, and when this is your pH, OH, and this is your tertiary butoxides. So it will transfer to this, and this will leaves out. This is the step. It is called transmetallation. And after transmetallation, what you get? So let us discuss. So up to this we discuss, that is PDL, this is your pH, O, TBU. So after transmetallation, what you get? This is PD, this is L, this is pH, and again there is a one phenyl is attached to this metal atom. So this process is called transmetallation. The first step is oxidative addition. Second, that is replacement of a bromine atom by the base such as potassium tertiary butoxide, and due to the weak bonding, it can easily replace the potassium tertiary butoxide. Tertiary butoxide is easily replaced by this negatively charged boronic acid. That is, the rate of transmetallation is very high. And then what you get here, L, PD, L, phenyl is there. And the next step is that the reductive elimination. So for reductive elimination, we can write this as PD. This is your L, this is your L, and this is your pH. This is your pH. And the last step of this Suzuki coupling reaction is the reductive elimination. So two cis ligands are removed from this complex. So what do you get here? So we get the bond between one phenyl and second phenyl, plus what you get here, we get the active catalyst, that is PD, and this is your L, and palladium having a zero oxidation state. So this is your reductive elimination. So this is your last step of this Suzuki coupling reaction. So the role of base is very important in this Suzuki coupling reaction. So what is Suzuki coupling? For Suzuki coupling, one of the partner is your halides, either it is saturated or unsaturated. Then the second partner is boronic acid, either it is sp2 or sp3, saturated or unsaturated. The catalyst, again, it is palladium. It is in zero oxidation state in presence of base such as potassium tertiary butoxide to get the final product. So what is the first step? In the first step, that is the 14 electron species PDL2, it will react with your unsaturated halides, that is bromobenzene, and it undergo oxidative addition to convert this PD0 into PD second, and we get a complex. So again we discuss L, PD, L, it is 0, undergo oxidative addition to convert into PD, L, one bromine is there and one phenyl is there. One bromine is there, one phenyl is there. Then there is a replacement of what? This bromine by this potassium tertiary butoxide. So we get this, that is L, one phenyl is there and one OTBU is there. Then there is a replacement, or there is a transmetallation. So the first step is oxidative addition. The second step, it is called hydroxypalladation. So replacement of this bromine by tertiary butoxide, it is called hydroxypalladation. The next step is what? The transmetallation. The next step is what? Transmetallation. That is transfer of phenyl from boronic acid to this palladium atom. So what do you get here? PD, L, this phenyl, and this phenyl is there. For reductive elimination, so we can rearrange the structure, that is PD, PP. So we can write this as, for reductive elimination, we can write this as PD, PH, this is L, this is L. So the ligand must be cis to each other. It undergo reductive elimination and we get the final product, that is the bond between one phenyl and second phenyl, and we get again the active palladium as a catalyst. So what are the different steps in Suzuki coupling reaction? The first step is oxidative addition. Second, a replacement of bromine by the base such as potassium tertiary butoxide, it is called hydroxypalladation. Third, transmetallation, that is a replacement of the base by the phenyl from the boronic acid, and the next step is the reductive elimination. So the role of base is very important in Suzuki coupling reaction. So why Suzuki coupling is very important? So there is no limitation for the halides and the boronic acid, either it is sp2 or sp3, it will give the product. So this is very important in organic chemistry. So this is all about Suzuki coupling reaction. In the next lecture we will discuss the next carbon-carbon coupling reaction, that is Negishi coupling reaction. Thank you.